Yeah.
Inflection. Okay, so we know we're going to have to differentiate. Hold on. Okay. So with a point of inflection, it's basically where the second derivative of the function must equal 0. So first of all, I have to assume, do you know, well, not even assume, I have to ask, do you know how to differentiate these functions? Because that's the first thing. So
Yeah, I know how to differentiate them.
Yeah?
Yeah.
Okay. So that in mind then, we need to work out the first derivative. So f prime x, this differentiated becomes, this is a chain rule, 2 cos of x to the power of 1 multiplied by the derivative of cos, which is minus sine x, and then that's minus 2 cos x. So that just simplifies to minus 2 sine x cos x minus 2 cos x. So that's the first derivative. And then to work out the second derivative, do you know you haven't done trigonometric identities, have you? Or have you?
Oh, we have.
Oh, do you know what 2 sine x cos x is the same thing as?
2 sine x cos x.
Yeah. If you did your compound angle formulae, double angle formulae.
Oh. Oh, isn't that is it that cos theta plus a?
Well, one of those.
Oh, is it the sine theta plus a?
Is it what, sorry?
Sine theta plus a.
Yeah, a variation of that. So if you have it in terms of x's, do you know what that is?
Oh, sine x plus. Oh no, sine x minus. I'm not sure.
This one is actually sine of x plus x.
Oh.
Which is the same thing as sine 2x. But when you expand it, it's sine x cos x plus cos x sine x, which is the same thing as 2 sine x cos x. But that's the same thing as sine of 2x. So in actual fact, this is the same thing as minus sine of 2x minus 2 cos x. And the reason that I've written it like that is because we're going to differentiate this again. I wanted to avoid using the product rule. So it's handy to know these identities because you can make work a little bit easier for yourself. So that's the first derivative. Now f double dash x or f double prime x is going to be this differentiated, which is going to be minus cos 2x multiplied by the derivative of 2x, which is 2. And then minus 2 cos x, well, that differentiates to plus 2 sine x. Then this becomes minus 2 cos 2x, that's a 2, plus 2 sine x. That being said, we now want to make this equal to 0, because for the point of inflection, it's just where your second derivative equals 0. So we let minus 2 cos of 2x plus 2 sine of x equal to 0. And we have to solve this equation. So firstly, we need to now use identities again to change this back into something that we do know in terms of cos. So that's going to be, well, first of all, let me get it to one side. So let's divide everything by 2, and let's take the cos x over to the other side. So if I divide by 2, I'm left with cos 2x plus sine x. Sorry, minus cos 2x plus sine x. And if I add cos x to both sides, I'm left with sine x equals cos of 2x. Make sense?
Yeah.
Cool. And then I have sine x equals, and then cos 2x, using my expansion for cos of a plus a, becomes cos squared x minus sine squared x. And then I have sine x equals, I can rewrite cos squared x as 1 minus sine squared
Wait,
x.
I don't understand. Where did cos squared x minus sine squared x come from?
It's using my identity cos a plus b, or in this case, cos x plus x,
Oh.
is cos x minus sine x sine x.
Oh, okay. I got that.
And then, yeah, so that's cos squared x minus sine squared x. Cos squared x is the same thing as 1 minus sine squared x. And then I've got the minus sine squared x still over here as well, the second one. Why have I done that? It's because I've now got an equation that's all in terms of sine. So I'm just going to write this on the next page. So I've got sine x equals 1 minus sine squared x minus sine squared x. And
Shouldn't
then
it be minus sine x?
Sorry?
Shouldn't it be minus sine x?
Why is that?
Oh no, okay, yeah, never mind.
Okay, cool. So we have sine x is 1 minus 2 sine squared x, because we just simplified the sines, minus sine squared x minus sine squared x. And then I'm going to get everything to one side and make it equal to 0. So I have 2 sine squared x plus sine x minus 1 equals 0. And I need to factorize. Can this be factorized? 2 numbers that multiply to give minus 2 and add to give plus 1. Oh, yeah, that's good. That's positive 2 and minus 1. So that's 2 sine x minus 1 multiplied by sine x plus 1. Does that work? So 2 sine squared x plus 2 minus sine. Yep, minus 1. Yep, that works. That factorization works. So it means that either sine x equals a half or sine x equals minus 1. But then we're not done. We need to work out all the values in the range 0 to 2 pi. Are you familiar with radians, by the way?
Yeah.
Cool. So with sine x equals a half, we get the x is equal to not 30 degrees, well, 30 degrees, but in radians, that's pi over 6. You can use either your calculator or a sine graph to just quickly verify your other solutions. So we've got this point here. So that's pi over 6. If this point is pi, then this point here is pi minus pi over 6, which is 5 pi over 6. And what's our range? It's between 0 and 2 pi. So we've got x equals pi over 6 and x equals 5 pi over 6. And then we've got sine of x is equal to minus 1. So from that, we get that x is going to have to be minus 90 or minus pi over 2, which I'm going to put in yellow, is over here. So the other graph, the other point where it's going to hit minus 1 is over here, which is 3 pi over 2. So x also equals 3 pi over 2. So we've got 4 different solutions there, but they're asking us for the points of inflection, i.e. A coordinate. So in particular, we've got to substitute these x values back into our f of x, which then gives us our y coordinate. So let me just write f of x over here. So what's that?
Yeah. Oh no, sorry, I was speaking to someone else.
No problem. So f of x is equal to cos squared of x minus 2 sine x. Yeah, just that. So now I need to substitute in each value of x into f of x to get out my other coordinates. So f of pi over 6, going from all my solutions, is equal to cos squared of pi over 6. So I know that cos of pi over 6, well, cos squared of pi over 6 minus 2 sine pi over 6, and I can put this in my calculator and it gives me something. So I don't have my calculator with me. Cos of pi over 6 would be root 3 over 2, square that. That is 3 over 4. Sine pi over 6 is a half, times that by 2 is 1, so minus 1. So that's equal to minus a quarter. So one of my solutions is x equals pi over 6. Y is equal to minus a quarter. So that's one of my points of inflection. Next, I'm going to have f of 5 pi over 6. So that one, what's that going to be?
Oh, should I work it out?
Yeah, that one's going to be, oh, what's cos of pi over 6? Cos of 5 pi over 6 even. I'm just thinking about it. Let me just put here. So cos squared.
I got cos 5 pi over 6 equals negative root 3 over 2.
Yeah, that makes sense. Cos squared of 5 pi over 6 minus 2 sine of 5 pi over 6. So yeah, that's negative root 3 over 2. So therefore, square that, that's still going to give you 3 over 4. Sine of 5 pi over 6 is a half. The minus 1, that's again equal to minus a quarter. So I have a solution for one coordinate at 5 pi over 6, comma, minus a quarter. And then I have my next one, f of minus pi over 2. Well, actually, no, f of minus pi over 2 isn't a solution because it's not in the range, is 0 to 2 pi. So I'm going to leave that one. I'm actually going to put 3 pi over 2 because that one is in our solution range. So what is 3 pi over 2? Cool. Okay, so that's 0. So that's going to be cos squared of 3 pi over 2 minus 2 sine of 3 pi over 2. And that's equal to 0 minus 2 lots of minus 1, which is equal to cosine of 3 pi over 2 is minus 1. That's going to be 2. So this solution, or this coordinate, is going to be 3 pi over 2, comma 2. So my solutions, or my answers, are going to be this, and this, and this. They're going to be my free coordinates as a result. So, yeah, this was a few steps, but it's all stemmed from the fact that the points of inflection is where the second derivative is equal to 0.
Yeah.
That's
Can
it.
we do one more?
Yeah. We can do, I guess, the other one that's there on here.
Can we do one that doesn't involve like trigonometry?
So the second one
Oh
doesn't.
yeah, this one. Yeah. Okay. Yeah.
Yeah. So with part B, we want to work out the derivative. So
Would you use quotient rule?
you could use quotient rule, I guess. Yeah, you could use quotient rule. I'm just thinking. I really don't want to use quotient rule. We'll do it, like, to get the practice of quotient rule. I'm really just thinking, is it worth doing quotient rule, or might it be worth just going into algebraic long division? Because I'm wary that we're going to have to differentiate this twice. No worries, we can do quotient rule to get the practice. So we'd let u be our numerator. So that's x cubed minus 2x squared plus x minus 1. So therefore, du dx is equal to 3x squared minus 4x plus 1, differentiating. And then we've got b equals x minus 2. So therefore, dv dx equals 1. And then our quotient rule is u... No, it's not. It is v du dx, take away u dv dx, all divided by v squared. So in this case, it's v, which is x minus 2, multiplied by du dx. So that's 3x squared minus 4x plus 1. Take away u dv dx. So that's going to be x cubed minus 2x squared plus x minus 1, all multiplied by 1. And that's all divided by v squared, which is x minus 2 all squared. Okay.
Can I get the Jamboard link, please?
Yeah.
Thank you.
You go. So yeah, this is one reason why I didn't want to do quotient rule, because I knew that they'd get all of this happening. And I know that I'm going to have to tidy this so that I can then get ready to differentiate this again. Does that make sense?
Yeah.
Why? So in fact, what I am going to do is on the next page, I am going to do algebraic long division, because differentiating this is going to be a nightmare. It's going to be so much work. I mean, either way, it probably will be a lot of work, but and also I miss. Well, that's fine. I can just put a minus in front of it. But yeah, if I do algebraic long division, I get x minus 2 into x cubed minus 2x squared plus x minus 1. So x into x cubed goes x squared. X squared times x is x cubed. X squared times minus 2 is minus 2x squared. Take away. I get nothing under here. And then x minus 1. And then x into x goes once. So that gives me 1 times x, which is x. 1 times minus 2 is minus 2. And then x take away x is 0. And then minus 1 take away minus 2 is 1. So now my function becomes f of x. Rather than writing that complicated one that I've got x squared plus 1. And that's just plus the remainder, which is 1, and then divide that by the divisor. So x minus 2. This is much easier to differentiate. Hopefully we agree. This is x squared plus 1 plus x minus 2 to the power of minus 1 for the sake of differentiation. Then we have f prime of x, which is 2x. 1 differentiates to 0. This x minus 2 to the power of minus 1, that's going to become minus 1 times x minus 2 to the power of minus 2 multiplied by the derivative of the inside, which is 1. Just that chain rule there. Tidying that up, I get the f prime of x is equal to 2x minus x minus 2 to the power of minus 2. Then differentiating this is nice as well. I get f double prime of x. So 2x differentiates to 2. And then this other thing that I'm differentiating becomes minus 2. So it's minus 2 x minus 2 to the power of minus 3, taking away 1 from the power, multiplied by the derivative of the inside, which is 1. So that simplifies to f double prime of x equals, so that's 2 plus 2 lots of x minus 2 to the power of minus 3. And then that's the second derivative. Then we need to make the second derivative equal to 0. So let f double dash x equals 0. And I'm going to rewrite this as 2 plus 2 over x minus 2 cubed, because that's what that is, with the negative power removed. Make that equal to 0. I'm going to multiply everything through by x minus 2 cubed. So I end up with 2 times x minus 2 cubed plus 2 equals 0. dividing everything through by 2, I get x minus 2 cubed plus 1 equals 0. Taking away 1 from both sides, I get x minus 2 cubed equals minus 1. And then cube rooting both sides, I get x minus 2 equals minus 1. So therefore, x is equal to minus 1 plus 2, which is 1. That's my x value. And then to get my y value, I just need to substitute x equals 1 into my original equation. So just do it in the bottom corner here. And I'm going to use this version of f of x that I got from my long division. So f of 1 equals 1 squared plus 1 plus 1 over 1 minus 2. And that equals 1 plus 1 and then plus 1 over 1 minus 2 is 1 over minus 1, which is minus 1. And then that becomes just 1. So my coordinate of my point of inflection for this one is 1, 1. And that is our final answer. Is that okay?
Yeah.
So again, it's the same steps, obviously just different methods of differentiation. But yeah, with these questions in particular, it is, I guess, important to try and find different ways of doing this. I just realized I made a mistake actually. All that. The one mistake I forgot to include was the fact that this is f of x is equal to minus all of this. So what I should have done is say that f of x was equal to minus all of this. So therefore, my second derivative would also be the negative of all of this. So I just have to put minus in front of everything. My second derivative being this equals 0. It doesn't change my x value, but it does change my y value basically. When I put it into f of x, instead of getting 1, I'd get minus 1. In actual fact, my coordinate is 1 minus 1. Does that make sense? What my mistake?
Yeah.
But again, the techniques don't really change. It's kind of the same. Just the only thing that does change is what do you call it? Yeah, the only thing that does change is going to be the technique. Does that make sense?
Yeah.
Cool. So there we go.